This is lesson 753 in The Scientific Revolution, Part 2, Scientific Laws, Experimentation, Observation, and Demonstration. And our history quote is this: "If history is any indication, all truths will eventually turn out to be false." Dean Kamen. And that does seem to be the case, doesn't it? We started off with Aristotle, and everything he said was considered to be true. He was truth, and then he turned out to be wrong about so many things. Then we had Sir Isaac Newton. Newton, who came up with Newtonian physics, and then we thought we had it right, and we had the periodic table, and we had chemistry, and things work exactly the same way every time. And then radiation was discovered, and then quantum mechanics was discovered, and subatomic particles, and it turned out that Sir Isaac Newton was not the whole story, not even close. And so who knows when that will actually end, if ever. So the big goals of the scientific revolution. First thing, empiricism. That is so important. Empiricism means reasoning by what you can actually observe and measure, rather than by faith in what you've always been taught. So you don't take anything on faith. Empiricism depends on two big things, like I said, experimentation and observation. Empiricism seeks to examine all of the traditional beliefs about the universe and to try to find a single set of natural laws that governs the universe. We call something a law, and I'll say this more than once, when it produces the exact same result, the exact same way, every single time, without exception. The truth of such a law can be demonstrated to other people. And one of the most convincing ways to demonstrate that something is a law is with math, the universal language. Like Galileo said, mathematics is the language with which God has written the universe. So let's go back to Johannes Gutenberg. He invented mechanical movable type around 1450. He arrived at the perfect time for Renaissance humanism. Humanism values eloquence and precision of expression. Movable type meant that everyone could read the exact same thing. Renaissance humanists could communicate with confidence that they were discussing the exact same ideas, using the exact same vocabulary. And when you have that kind of setting, some ideas are going to win and some ideas are going to lose. And humanists could do all of this much more cheaply than ever before, thanks to Gutenberg. The Gutenberg Bible, one of our textbooks, puts it like this: printing gave hundreds or even thousands of people identical books, allowing them to more easily discuss the ideas that the books contained with one another in person or through letters. Guess who told everybody what the universe looked like? Aristotle. Aristotle provided the basic foundation of people's knowledge about physics, and he taught that there were four imperfect and corruptible elements on the earth: earth, wind, fire, and water. So everything on earth was made up of some kind of combination of those four things. He taught that the heavens were made of a fifth element called quintessence that was perfect. In fact, the word quin means fifth, so it's the fifth essence or the fifth element. Quintessence had two properties to it that the other four earthly elements didn't have. Number one, it was perfect, and number two, it was unchanging. Aristotle taught that all the heavenly bodies rotated around the earth, and this was called the geocentric theory. Aristotle taught that all of these heavenly bodies were embedded in an interlocking series of crystal spheres above the earth. He called them crystal spheres. You can kind of think of it like one of those Russian babushka dolls, the way they're interlocking and one is inside the next and inside the next. There's no space, there's no vacuum in Aristotle's model. And of course, everything up there is made of quintessence. The Catholic Church had been teaching Aristotle's ideas for centuries, so they had a lot invested in geocentrism. Aristotle's crystal spheres model, when you look up at the night sky, it actually makes a lot of sense. What can we say about crystal, like the crystal that you might have in your house? It's perfect, it's solid, it's unchanging, it's transparent. You can embed things in it. That's how you like decorate it and stuff like that. It's invisible. Solid layers of crystal around the Earth makes sense. And it explains why some objects move congruently and some don't. For example, the stars appear to move, and they all appear to move together in the night sky. So they must exist within some kind of an invisible unifying structure, right? Makes sense. And like I said, there's no such thing as space up there. So the heavenly bodies are all actually quite close to you. When you account for all the different movement patterns of all the heavenly bodies up there, and you're using this crystal spheres model for your conception of the universe, then you come up with about 10 of those spheres all interlocking. And then beyond them, beyond the last one, the top one, you have heaven. And that was the structure of the universe as Aristotle understood it and taught it. Then along came Copernicus. Copernicus was an advocate of the heliocentric theory, the idea that the Earth goes around the sun, not the other way around. And his work on heliocentric theory was called On the Revolution of Heavenly Bodies, which was published in 1543, about 26 years after Luther's 95 Theses. Copernicus was a Polish guy, and he published his book on his deathbed. He waited until he was about to die to publish the book, not because he was afraid of what the church might do or how the church might react, but because he was afraid his colleagues would laugh at him. But there was a problem with heliocentrism. When you observed objects in the sky, their movement patterns didn't quite fit the theory. Then in the 1570s, two important phenomena occurred which brought Aristotle's crystal spheres idea and model of the universe into serious doubt. In 1572, a new big star showed up in the sky out of nowhere, and it shone brightly for 2 years and then disappeared. Now today we know that that was a supernova. Then in 1577, a new comet entered the solar system, and it cut a path straight through those crystal spheres. Those crystal spheres, if they were truly there, didn't even seem to slow this thing down. These two things, this big new star coming out of nowhere and this comet cutting through these crystal spheres, weren't supposed to happen if these crystal spheres that were going around and around the Earth were of this perfect, unchanging quintessence. Then there was Tycho Brahe, and he lived from 1546 to 1601. He was Danish, and at the beginning of his career, Brahe made close observations of that big new mysterious star. And his observations impressed everybody, and the Holy Roman Emperor at the time, Rudolph II, set him up with his very own observatory. Brahe worked for the church, and he collected massive amounts of data over the course of 20 years, and he developed what was called the Rudolphine tables of planetary motion, named after Rudolph. The problem, however, was that the observations didn't add up mathematically. And then Tycho Brahe died, leaving his assistant, Johannes Kepler, to make sense of all of this data. So now we have Johannes Kepler, 1571 to 1630. And Kepler managed to get the Copernicus idea and the Brahe data to make sense with his 3 laws of planetary motion. All you have to do to understand the 3 laws of planetary motion is to have played with a yo-yo. If you can imagine a yo-yo, you can get all 3 laws of planetary motion. So the first one is this: planets' orbits are not circular, they are elliptical. And if you've ever played with a yo-yo, you know that the orbits of the yo-yo around your hand are very often elliptical, aren't they? Second law was planets don't move at the same speed all the time. Instead, when it's far away from the sun, it slows down. When it comes back around to the sun, it speeds up. Imagine a yo-yo. Imagine like your hand is the sun. You know that when that yo-yo is far away from your hand, it slows down, its orbit slows down. But when it comes back around close to your hand, like if you're doing walk the dog around the world or whatever the tricks are for yo-yos, you know that when it comes back around your hand again, it speeds up. That was the second law of planetary motion. The third law was this: how long it takes a planet to complete an orbit around the sun is precisely related to its distance from the sun. That's easy to visualize too. If you've ever played tetherball, think of tetherball. When the tetherball is far away from the pole, it takes a long time to go around that pole. But when it starts to tighten up and it's closer to the pole, you know what happens. It starts going around that pole faster and faster and faster and faster. That's the third law of planetary motion. We call these laws because Kepler didn't just claim these things, he was able to convincingly demonstrate these things with math. And he also came very close to formulating the law of universal gravitation. Newton wound up doing that later, in large measure by studying Kepler. Galileo Galilei, 1564 to 1642. Galileo was a total science guy. He loved science. He loved everything about science. He loved the observation. He loved the experimentation. He loved demonstration. One of the things to understand about Kepler's laws of planetary motion is you would think that would really bother the church, but it didn't. And the reason it didn't bother the church, the reason the church didn't get too excited about Kepler's 3 laws of planetary motion, was that even though he had managed to prove that these were laws, he still couldn't explain the mechanics of why planets moved in the first place. If you could do that, then the church would get pretty nervous. And Galileo formulated the law of inertia. Like I said, we call something a law when it produces the exact same result, the exact same way, every time, without exception. And the law of inertia states that an object is at rest only under very specific conditions. And if those conditions are not present, then those objects are much more likely to be moving perpetually. To demonstrate the law of inertia, Galileo conducted motion experiments using balls on a flat, hard wooden surface. And this is because you would have minimum friction acting on that object. Galileo was also an accomplished instrument maker, and he built his own telescope based upon a written description of one that he had gotten. With that telescope, Galileo found 4 of Jupiter's moons. Remember that Aristotle had said that the planets were all embedded in solid crystal spheres that surrounded the Earth. And Galileo argued that Jupiter couldn't possibly be embedded in a crystal sphere if it had moons moving around it. Galileo studied our moon's surface and he found it to be covered with ugly, imperfect craters. And remember that Aristotle had said that everything above the Earth was made out of a 5th element called quintessence, which he said was perfect and unchanging. And Galileo argued that the moon couldn't possibly be made out of such a substance as quintessence because its craters showed that it was imperfect and always changing. Then we come to Sir Isaac Newton, 1642 to 1727. He was extremely focused on math, and he did something amazing at the tail end of this scientific revolution. He took all the scientists that we've discussed so far, Copernicus, Kepler, Brahe, and Galileo, and he did something revolutionary. He synthesized all of their teachings into a unified set of mechanical proofs. And in 1687, Galileo wrote The Mathematical Principles of Natural Philosophy. In this book, Newton formulated the law of universal gravitation. He said gravity works the same way, everywhere, every time, without fail, no matter where in the universe you are, whether you're up in space and you're talking about planets, or you're talking about an apple falling to the earth, doesn't matter. And he also said that you can calculate the amount of gravitational force perfectly. It goes up with mass, down for distance. The scientific revolution wasn't just about space. It was also about medicine, the body, and chemistry. And we begin with William Harvey, English person, 1578 to 1657, physician. He was another proponent of experimentation. And in 1628, he discovered the circulation of the blood through veins and arteries, and he explained what the heart did and how it worked. And he disproved the theories of the ancient Greek doctor Galen, whom people had believed for centuries. Galen, to make a long story short, is kind of like the Aristotle of medicine. Robert Boyle, English, 1627 to 1691, a physicist. He was also a huge advocate of experimentation. He developed modern chemistry, and he helped found the great scientific organization, the Royal Society, in 1660. He used experimentation to discover new elements, and he actually created a vacuum. People didn't think you could. People weren't sure a vacuum existed at all. And he discovered Boyle's law, named after him, which said that the pressure of a gas varies inversely with the amount of volume it occupies. Here's a famous painting of a scientist killing a bird by placing it in a vacuum. These guys also created new technology. For example, the microscope, which led to gains in biology, and the telescope, which led to gains in astronomy. The results of the scientific revolution. The West became the most vibrant center for scientific advancement. And they followed earlier examples in China, classical Greece, and post-classical Islam. New governments sponsored new research facilities. They saw the gains that could be made through the scientific revolution. There was a ripple effect. There was a cultural reorientation away from religion and toward science. The senses and reason became more important than faith. Doctors became more important than mere healers. And natural laws became more important than miracles. God's role was simply to set natural laws in motion. And human nature was basically good. People could control and calculate their environment. Science could research, test, and disprove long-accepted theories. And scientific knowledge became something to be proud of. Science and religion. All of these scientists that we've talked about, Brahe and Kepler and Copernicus and Galileo and Newton, they were all, to a man, deeply religious. They saw their work as God ordained. Their attitude was, God gave me this mind and this curiosity. He must want me to reveal his glory. But heliocentrism presented a problem. Why would God create this universe and not put man, his most amazing creation, made in his own image, dead center? All the major religions, not just the Catholic Church, all major religions had problems with heliocentrism. The Catholic Church was slow to react to this heliocentric theory at first, but in 1616, the Holy Office of the Catholic Church got involved in the issue. And the Holy Office was the central official church body that investigated heresy and unsound teaching. And the Holy Office put all of the books that advocated heliocentrism on their index of prohibited books. This was a list of books that good Christians weren't supposed to read. Galileo stayed quiet until 1623. But then his friend Urban VIII became Pope. Urban VIII was actually a pro-science guy. He loved science. So Galileo felt safe publishing again. But in 1632, Galileo wrote a book which blatantly ridiculed and made fun of people who believed in geocentrism. And that was too much for the church to take. In 1633, Galileo was put on trial by the Holy Office, and he was threatened with torture. And he was forced to publicly renounce and curse his Copernican errors, that being heliocentrism. He was placed under house arrest for the rest of his life, about 9 more years. The Catholic Church became more hostile towards heliocentrism for some time after that. This is another look at that very famous painting that we already saw in a Google form. This is Hans Holbein the Younger's famous 1533 painting called The Ambassadors. And this painting brings together several things that we have been learning. We've been learning about the Renaissance. We've learned about the Reformation. We've learned about exploration. We've learned about the scientific revolution now. And this painting brings all of these elements together in one work. Keep in mind that the idea of an ambassador was a product of civic humanism. That was something that civic humanists invented, the idea of sending a resident ambassador to other countries. The technical detail and the symbolism of the Northern Renaissance is reflected in this painting. And between these two guys, one guy is secular, the guy holding the telescope, and the other guy holding the cross is clergy. And the top shelf is actually filled with navigational and scientific instruments, including an exotic rug from some discovered place. And the lower shelf is filled with religious things like a lute and a Lutheran psalm book. But both shelves, each one has a globe, because you're not looking at one ambassador, you're looking at two. You're looking at a Renaissance scientific exploration ambassador, and you're also looking at a religious ambassador taking his beliefs out to the entire planet. So he's got a globe on his shelf also. And then that weird-shaped skull at the bottom is a symbol of mortality. Now, you might think that somebody superimposed that as some kind of a JPEG or something onto the image, but that's not. That's actually part of the painting. The painter did that.